Today we are in section 2.5. We have been working on the derivative rules, and today for 2.5, this is higher order derivatives. When you are finding the derivatives of a function, we have what is called the first degree, and that's what we've mainly been working on. So of course we've seen it labeled as a function with the prime symbol. You could have y prime. It could be written this way. So we've looked at different ways to write it. And now what we're going to look at is taking that to higher levels. So then we would have the second degree. And basically what that means is the second degree, so there's two primes. And in essence, you're taking the derivative of the first derivative. And knowing its second degree is because there's two prime symbols. Here it would be d squared y, d squared x. Now, of course, we typically use these, but this is correct as well. Now, that you could just keep going, etc. So then you could take the derivative of the second, so third degree, you could have three prime symbols, or once it starts getting to higher degrees, you can actually use numbers instead of the prime symbols. So let's look at an example. So the original function of 4x cubed minus 6x squared plus 5x plus 7. And so if we were going to find the rate of change for that, or the first derivative, of course, we're going to use the rules that we have learned previously. So we would have 12x squared minus 12x plus 5, and of course, the derivative of 7 is 0. So this would be the rate of change. Then the second one would be the, rate of change of the rate of change, which seems like a mouthful. So, sorry, I'm trying to mess with my light. So basically that's just saying the second degree or the second derivative. So we're going to take the derivative of the first derivative. So 2 times 12, so we get 24x minus 12. Then you could continue on. The third derivative, you could put 3 prime symbols, or you could put 3 to know you're doing the third derivative, which would be 24. And then the fourth derivative, of course, would be 0. Now, we could continue taking its derivative. I mean, we could take the fifth derivative, and the derivative of 0 is 0. So we could keep going until the 30th derivative, but we know from 5 to 30, it's just going to continue to be 0. All right, so that is just how that looks, taking the first, second, third, and so forth derivative. Okay, so I don't think I'm going to have enough room on that page, so I'm going to go ahead and start. We're going to do an example. All right. Say we have the function f of x equals 1 over the square root of x. Now, something that you will see if you're doing practice problems from the ebook, or when you get to the WebAssign, it may read something like, find the second derivative of x for, whoops, I should have, now let me rewrite that. The second derivative for 1/9. So in essence, what that means is we need to find the second derivative of x, and then we'll substitute 1/9 in for it. Now, before I just jump into the first derivative, I want to rewrite this. So I'm going to rewrite the function as x to the negative 1/2. Now I'm going to take the first derivative, which would be negative 1/2 x. Negative 1/2 minus 2 over 2 is negative 3/2. So there's the first derivative. And we need to find the second derivative. So we will have negative 1/2 times negative 3/2 x to the, and here you would have negative 3/2 minus 2 over 2, which would be negative 5/2. So I'm going to clean it up a little bit. We know negative times negative is positive. So we would get 3/4 x to the negative 5/2. Now, you could clean this up if you wanted. You could put it 1 over x, and then this becomes positive. But realistically, we can put it into our calculator here. And I'm going to show you how if you don't know how to do that, because we have the second derivative. Now we want to find that for 1/9. So I'm going to have 3/4 times 1/9 raised to the negative 5/2. Now, at this point, you can put it into your calculator. So we would have 3 over 4 times, and then I'm going to put 1/9 in parentheses. And I'm going to raise it. It is this up arrow. And then in parentheses, or not in parentheses, do the fraction and have negative 5 over 2. And we get 182.25. And then, of course, depending upon what the answer is or how WebAssign wants it, I can push this double arrow and it'll convert it into its fraction, which is 729/4. Because we know this is 182 1/4. If you take 4 times this plus 1, so you'd get 729/4. So either this or this, just pay attention to WebAssign as to what it wants. I'm going to guess it might want this, but I'm not 100% certain. Okay. All right. Now, that's an introduction as to what derivatives of higher order are. Now we're going to talk about what it's actually used for. Okay. So what I want to talk about now is distance, velocity, and acceleration. This is where this is used in real life situations. Okay. All right. So I think, well, let me do this first. All right. So the original function, so instead of f of x, I'm going to put s of t because it's going to be what you see in the book, okay? So this is your distance at time t. Distance at time t. So let me give you a little visual. Hang on for just a second. Okay, sorry, I was messing with something on my computer. I was just curious. Okay, so I guess the only way I'm going to want to look at this, give me a minute while I kind of try to make this a little bit bigger. All right, so here we have an X and a Y axis. All right, so the input is T, which is your time. So that could be seconds, that could be hours, whatever it is. All right, so we're going to look at hours. So here I'm going to put is 1 hour of drive time. And here would be represent 2 hours. Output is the distance that you have driven. So input is time, output is distance. So let's say that right here is where we start, and this is Enid. And let's say that we're traveling here, and we're going to say this is Tulsa, because Tulsa, depending on where you go, is about a 2-hour drive from here. All right. So if I leave my house, and I'll talk about this a little bit. Whoops, meant to do this. So disregard that, my hand got. Okay, so I leave Enid, I'm driving through town, I hit the interstate, and then I'm driving into Tulsa, and I get to my destination about 2 hours, and this would tell you that the distance that you drive. All right, so that's what we're looking at as far as input and output. So let me go to this. Sorry. Okay. So example, like I was saying, is say in 2 hours, I drove 116 miles. All right. So that would be just kind of an example. So your input is 2 hours, output would be your 116 miles. So your original function deals with distance. All right, so now we're going to start getting into the higher order. So the first derivative is also known as v of t because we're talking about velocity. In essence, your speed at a particular time. Now, remember that the first derivative tells us the slope of the tangent line. So we know a slope can be positive or negative. So since what that tells me then is the velocity can be positive or negative. Now, this is where you need to be careful. We're not saying you drive negative speed, but we're talking directional. So this could be positive or negative because it's dealing with your slope, which is directional. So if I have a positive slope, that tells me which direction I'm going. And then if your slope becomes negative, that would tell me your direction is now going. So like if you're driving north and then you got a negative, that means now I'm driving south. And so concerning, or how that relates to our picture, dealing with speed. So after 1 hour, here would be a half of an hour. So when you start out in Enid, if I'm still in town, I'm driving slower. And then as I get to the edge of town and I start leaving town, my speed picks up. At 1 hour, I'm driving, you know, on the interstate. So I have a higher speed. And then as I get to Tulsa, my speed's going to slow down because now I'm back in town. So that's what we're talking about as far as our picture goes, or our graph. All right. Then, so distance is s of t. Velocity is the first derivative. So it stands to reason that acceleration is the second derivative. So that is the second derivative, which is also known as a of t. So in WebAssign, if it asks you to find the velocity of t, you know you're finding the first derivative. If it asks you to find the acceleration of t, you know it's asking you to find the second derivative. So this deals with acceleration, which here we're talking about if you were speeding up at a particular time, or if you were slowing down. So as you're leaving town, your acceleration would be speeding up. And then when you get into Tulsa, you would reduce your speed. So acceleration would be positive, reducing would be negative. Now, this I showed you deals with in 2 hours, you drove 116 miles. If you recall on the first derivative, that slope, it also means per. So this would be labeled something like 70 miles per hour. And when you get to acceleration, it's however many miles per hour per hour. So the way we label that is miles per hour squared. So that's some labeling that you need to be familiar with, okay? All right, so we are going to do an example with distance, velocity, and acceleration. All right, so what we're going to look at is the movement of a yo-yo. And its function is given to us as s of t is equal to t cubed minus 6t squared plus 5t plus 30. And the domain is from 0 seconds to 4 seconds. All right. So I've already put this into Desmos. So let me share that. All right. So let me go out for a little bit just so you can see. So here's 0, 2 seconds, 4 seconds. So you can see we're just going from 0 seconds to 4 seconds. So I wanted to give you that. And here is what we, whoops, went too close. Now here's what the 30 is. That is your number of inches from the ground. All right, so if you're standing up and you're holding the yo-yo at 0, then the yo-yo from the ground to your hand is 30 inches. And then of course we know a yo-yo, you first go up and then you let it release it down. So that's why it starts out going up and then it will go down. And then once it hits down, it'll start coming back up. Okay, so that is what it looks like as the yo-yo's movement. All right. So let me go back here. All right. So the first thing that we want to look at is distance. And we're going to do this at t equals 3 seconds. So let me write over here. Remember, t in this is seconds. And output is inches from the ground. Okay. All right. So distance is your original function. So we're going to do s of 3. So we have 3 cubed minus 6 times 3 squared plus 5 times 3 plus 30. And so, of course, that's going to be 27 minus 6 times 9 plus 15 plus 30. So you can put all of that into your calculator and you're going to get 18 inches. All right, so interpretation, because we know that WebAssign asks for it and you need to be able to interpret your findings. So what that means is in 3 seconds, the yo-yo is 18 inches from the ground. Because what we know here is we inputted 3 seconds and it outputted 18 inches. So let's take a look at, sorry, I have an alarm going off. Okay. All right, so I'm going to input, or I'm going to put the point 318. All right, so as you can see, here is 15, 16, 17, 18. Here is 1, 2, 3 seconds. So once you start the yo-yo at 3 seconds time, it is now 18 inches from the ground. So we started out at 30 inches. It has now gone downward, and at 3 seconds, it is 18 inches from the ground. All right, so that is what the first derivative tells us. Or I'm sorry, we haven't done derivatives, sorry. That is the distance, so that is the first function. I was thinking ahead because now we are going to do the first derivative. All right, so the next thing that we're going to look at is velocity. At 3 seconds. Well, at t equals 3. All right. So velocity tells me I need to take the first derivative, because remember, velocity is the first derivative. But I'm going to label it as v of t, but that basically means take the first derivative. So I'm going to come up here to my original, and I am going to take its derivative. So that would be 3t squared minus 12t plus 5 plus 0. All right, remember that the first derivative tells us the slope of the tangent line. The slope of the tangent line. So this is telling us the direction that the yo-yo is going. So I'm going to do this at 3 seconds. So we would have 3 times 3 squared minus 12 times 3 plus 5. And so this is 3 times 9, which is 27, minus 36 plus 5. So you get -4. So yeah, distance was 18 inches. Now we get -4. Now, what I want you to remember is this is the slope of the tangent line at 3 seconds. All right, so first I'm going to go, and I also have this here. Let me get this close. Trying to focus it up. Okay, so at 3 seconds, it was at 18, so that is right here. So there's 318-ish. Needs to be down just a little bit, okay? So our tangent line, the equation of the tangent line is going to be something right here. So it's saying that -4 is telling us the slope of this. And if you look, this is going downward, right? So at this point, that line is going down, which means it has a negative slope. So that makes sense. So let's take a look at that. I'm not going to go through the working out of the tangent line, but I did that earlier, and I know y equals, and again, the slope is -4x plus 30. Oh, I wish it was a different color. I don't know why it's not, but if you'll see right here, here is that tangent line. And at this point, it is going downward. And so that all makes sense. Trying to get it focused up. Okay, so that is the velocity. And so the interpretation of that would be the yo-yo is going downward. How do I know it's going down? Because of the negative at a rate of 4 inches per second. 4 inches per second. Okay, so then lastly, try to get this all on one paper. We're going to look at acceleration. At t equals 3. Now, acceleration is the second derivative. So I go to the first derivative, and now I am going to take the second derivative, which would be 6t minus 12. And we're going to do that at 3 seconds. So 18 minus 12, so we get 6 inches per second squared. Okay, so because this is positive, if you recall, acceleration is either speeding up or slowing down. Since it's positive, we know the yo-yo is speeding up. If it was a negative number, then we would know the yo-yo was slowing down. So at 3 seconds, the yo-yo is accelerating at 6 inches per second squared. All right, so that gives you a good introduction on higher derivatives, higher order derivatives. So that should give you good information for 2.5.